I'd like to welcome everybody to the ASME January. Hey guys, we're getting started. January 2023 joint meeting with the ASME Apollo rotating equipment section and the ASME gas turbine section. Okay, just a couple of things. We promote on Apollo all rotating equipment. We kind of exclude gas turbines and let the gas turbine specialists speak about that. But everything else, rotating and reciprocating, from design, installation, maintenance, we cover. Welcome everybody to the meeting. You don't have to be a member to attend, and you don't even have to come in a business suit and tie to attend. Okay. So tonight we're meeting here in person and Zoom at the Johnson Control Facility in I'm going to say Northwest Houston. Okay. This is the Apollo leadership team. These are the volunteers who help put together the meetings that we've been having. So I'm the chairman, Mark Crawford. Lauren Ferlden is the vice chair. Joe Marino is the treasurer, which is the hardest job. Next hardest is the secretary, Ivor Zimpapa, and Mashima Wilsonani is programs chair. And then we have Edison Lampson and Ellen Gillespie helping out on this. So you can be an officer with the function or just help at large. Okay. That's how you can contact us. So you can send us an email if you want to get on the email distribution list. If you want to be a speaker, you can volunteer by contacting one of us so that we can try to put you into the program chair cycle. Also, if you want to host a meeting at your facility and give a shop tour, that's how you can reach us and help set it up for your company. Okay. This is the gas turbine leadership team. We got Jeff Mountain is chairman. Vice chair is again Lauren Serlden. Treasurer is Colleen Remiger. Secretary Gautam Cheever. I'm sorry. Okay. Okay. I'm program chair, and then we got the same basic people, members at large. So we're always soliciting volunteers to help out. So a lot has been double dipping to keep it going. Same thing here. If you want to be a speaker or host a meeting or get on the email list, these are the ASME gas turbine emails that you can send to get involved in our chapter. Okay, before we get started, we're coming up on the point for asking for volunteers for next year's officers. So that'd be the 2023-2024. You get started July 1 and you finish the next June 30th. So we're seeking nominations if you want to volunteer. We'll talk about it in March at our next meeting in person. And then we have to vote for officers in the May meeting. If you don't show up, you get voted in. Okay. All right. And to be a leadership team member, you have to be an ASME member. So you do have to join to be a volunteer for it. You have to sign a volunteer agreement that you're going to adhere to the ASME rules. And again, the year starts 1 July and goes to next June 30th. And you get to vote in all the section materials because we do have to get together to try to organize. So we're the primary contacts with the ASME to try to facilitate events and going on in the area. Okay, the next. Oops. Should the page up and take it. Okay. The next ASME Apollo meeting is the 8th of March. It's at Lone Star Blower. I don't have the topic or location to give you right now. In May 10th, we're going to have one by our treasurer, Joe Marino. He's going to talk about couplings, which is what he enjoys doing so much. Okay. For the gas turbine, we're going to meet at the University of Houston College of Technology in Sugar Land. Don't have a topic or date on that yet. And then in May, we're going to do a meeting at Siemens Energy at Telegi Road. So again, we'll be setting the agenda and the date and everything later. So is there any other news that you need to present out at this time or things of interest?
The next two Apollo meetings are already on Eventbrite. So
Yep.
get your tickets now. Yes, turbine is still.
And the tickets you can either do in person or Zoom.
Will the gas turbine be on the same place that Apollo is?
It is.
Okay, we're kind of joined at the hip in almost everything.
We try to coordinate subjects and everything so that they relate together. So they do the gas turbine, we do everything else that they attach to. Okay. The next one's just some websites that if you link into it, you can keep up with the events and the calendar. Next. This is actually the real website information there that you can put on your computer or phone and see what's going on. Yeah, well, hopefully they get a copy of this. All right. The background for this is, of course, everybody's in the news about energy consumption increasing, and the U.S. Energy Information Administration, EIA, is projecting that world energy consumption will grow another 56% between 2010 and 2040. So, of course, to do that is that natural gas is the fastest growing fossil fuel, and they're expecting a 1.7% increase for that. So higher demand means higher cost in the future. So, of course, gas turbine generators are the most environmentally clean way to generate electricity using a fossil fuel. To meet the growing demand for power, adding additional gas turbine generators seems like a logical conclusion. And then the problem with gas turbines is nobody wants it in your backyard. And also it's a very capital intensive and very long permitting to get it all done, even though it is cleaner burning. So the speakers tonight is Randy Barnett and Mike Kennedy, both from Johnson Controls. I'll let you talk about yourself.
Great, thank you. So. I'll lose my,
I think we still don't want to share, but you're doing your presentation up there.
so how do I go back to that?
Lower on, sort of at the bottom, there should be screen share.
To the green one.
The green.
You pick your presentation.
Share the whole screen or just the presentation. How many are online? Just two?
I think there, how would I,
Oh, maybe. Yeah, I think it's just two.
looks like there's three.
Oh, yeah. one minute.
Okay. Okay, so I guess everyone can hear me speaking online, that the three are online. Thanks for the introduction. My name is Randy Barnett. I've been in the industry about 37 years. I don't have as much gray hair as I should, but I am losing quite a bit of it. My wife tells me every day. I lead Johnson Controls efforts with all the major energy firms, EPC firms, oil and gas companies, not just in the United States, but internationally. So my team, we work with the EPCs in the early pre-feed, feed stages, all the way through EPC and contracts on LNG projects, any kind of sour gas treatment projects, process cooling. We get involved with a lot of things that you'll learn about here. So we usually work with these different entities for some period of time. And then we are also the liaison to our out of country or out of town offices if they're in North America for on-site services, support, parts, warranty, etc. So we're kind of the quarterback. We have our hands in a lot of different things. So, we're going to show you some examples of different things that we do, but also our competitors can do as well. So this is not going to be a Johnson Controls used car sales pitch to you guys. We're going to try to keep this industry neutral. And I've forewarned Mike on this as well. Mike has been in the industry about 6 or 7 years
30 and
shorter than me. Ironically, we both went to school in North Louisiana at Louisiana Tech University. Go Bulldogs. I'm a mechanical engineer. Mike's what the hell are you?
electrical and computer.
Electrical and computer. He's milliamp man, I'm heavy metal. Some people call us Batman and Robin. All right, but we kind of together lead our team and we're involved with a lot of different things. So I'm going to start the presentation. The purpose of this presentation it's twofold. One is the benefits of gas turbine inlet air chilling and why that's important. We'll show you some examples, some reasons for that. We'll also talk a little bit about sour gas treatment, which is another thing that we do. We see that more and more, feed gas treatment. We're also going to talk about systems integration, cybersecurity, huge issue that a lot of EPCs and these oil and gas companies are facing these days. And Mike's going to touch primarily on that. And what you'll see is I'm going to talk more about the heavy metal stuff, and I'm going to hand off to him on the milliamp stuff. Okay, so at any point, you guys stop and ask a question, and we'll try to field it as best we can. Now, I'm going to try to use this mouse. My battery keeps going in and out, so I don't know what's going on.
So it's milliamps.
Hey, milliamp. Man, it's working. It's got full power.
That's because you did all that.
All right, I'm gonna go old school. Okay, let's talk about simple. This is at least the light works on. Yep, light works. Hey.
See, I made it work.
All right. Okay, so first thing, real basic. I know sometimes at these ASM meetings we have some students from the local universities that sometimes call in or participate. So first thing I want to do is keep it real simple. A simple cycle gas turbine. This is a schematic of a simple open cycle single shaft turbine. In this case, the ambient air is entering the compressor, which is where it gains energy. Then it travels to the combustion chamber combustor, where it mixes with the fuel. Okay, this mixture is a pressurized hot gas that then enters the gas turbine, which causes its wheels to obviously rotate at very high speed. Okay, so a couple of notes, and this is per ASHRAE, our sister organization, Systems Engineering Handbook. Typically 65% of turbine energy drives the compressor and engines accessories, which leaves only 35% for useful output. That's a very important item to remember. The temperature of the exhaust gas leaving the turbines is usually in the 1,000-degree range, with the airflow of 10 to 15 standard cubic feet per minute per horsepower. Now, these values depend on the engine model and different operating load that you're dealing with, but that's kind of just some rule of thumbs. So there's really two basic types of turbines that we see in the industry. There's industrial turbines, which we'll consider heavy duty. Okay, those are typically a single shaft, and they get to be pretty big, up to 130 megawatts in power. And those are either natural gas or oil fired. Okay, typically constant speed. What we normally see in the LNG world, like an LM6000 for my friends at Baker Hughes, they're aeroderivative turbines, which are jet engines. Okay, and I heard Lauren talk about it earlier. Those are multiple shafts. Instead of a single shaft, there are usually multiple shafts, independent shaft per turbine and its generator. Okay, Their ranges get up to about 40 megawatts. You have some mini turbines that get pretty low. And these are using natural gas. Okay. Now there's one turbine that I'm not showing here, which is some new technology, and that's electric turbines. Okay. Okay, no gas. Okay, so electric turbines don't have inlet air chilling. They don't need them. Okay, they're pretty damn expensive though. Okay, so there's, depending on who you're dealing with, in which culture you're dealing with, and if you're a Democrat or if you're a Republican, okay, then some people are promoting electric, some are still promoting natural gas. My personal opinion is natural gas is the right fuel source. All this stuff about going electric cars and all that, you got to get the energy somewhere. And so you want to kill Peter to pay Paul. And you worry about environment, you got to look at all the things that go into electric cars. Okay, and same thing's going on in our industry. Okay, so I won't get political on you other than to make that statement. Okay, so the bottom line, the natural gas, and these are usually variable speed applications. Okay, now a couple of things with these. Usually the inlet air temperature is in the range of 40 to 50 degrees Fahrenheit. Okay, an economics analysis will usually indicate what's your optimum temperature. Okay, when the Bechtels of the world and the Kiewits of the world and Shell and ExxonMobil, when we're working with those guys, it's always a system analysis. What is the right temperatures to get the inlet air to, and how much turbine capacity can we gain by making the temperature colder? And we'll get into that here in just a minute. It's always an economics analysis. Okay, so the purpose of gas turbine inlet air chilling. Again, definition of turbine, mechanical component, in which the energy of a working medium is converted to mechanical energy by kinetic action of a rotating element. That's a lot of words. That reminds me of my system dynamic days when we were taking that course at Louisiana Tech University. I made a C in it, but boy, God, it was hard. All right, so there's different types. There's steam and there's gas. Okay, heat rate. Heat rate, a couple of very important terms here. Heat rate, the unit fuel consumption of the gas turbine. Usually it's expressed depending if you're using international units or metric units. It's usually expressed in BQs per horsepower hour, BQs per kilowatt hour, based on a higher heating value of the fuel. It measures the system electrical efficiency. Now there's two types. Higher heating value of the fuel, that includes the heat of condensation of water. The lower heating value does not. That's called the net heating value. Very important that you notice the difference between these two, because there's some marketing games played out there by some of the lower tier turbine suppliers. Baker Hughes plays it straight up. When they tell you net heating value, they're talking about the lower heating value, just as an example. So turbine manufacturers, again, should be quoting you turbine fuel consumption based on lower heating value. Remember that. So combustion gas turbines, rotary prime mover in which a gaseous working medium, in this case it's air, is compressed, heated, and expanded to produce useful power. Again, we're back to system dynamics. ISO, International Organization for Standardization, kind of like in the traditional air conditioning industry, we have something called AHRI, which stands for the American Heating Refrigeration Institute. They have standards that all manufacturers are rated against. This is a common condition. Same thing with gas turbines. That's the ISO standard. Okay. And so the normal rating condition is the inlet air is at 58 degrees dry bulb, 60% relative humidity at absolute pressure, 14.7 psi, or if you want to do it in inches of mercury. A power factor of 90%. Other rating methods that are used: normal rated power, which is what the aircraft turbine people use. Industrial turbine manufacturer, they rate them at 1,000 feet of elevation, inlet air 80 degrees. Normally, it's because of their applications kind of lend themselves to different type of processes. So they usually operate at higher temperatures anyway. That's why they rate them that way. And then cited rate power. This is actually requires some calculation time to put together. Okay. Additional information, just some definitions for the college folks that might be joining us. Pressure ratio, that's the ratio of the highest pressure at the compressor discharge to the lowest pressure at the inlet. Adiabatic head, the energy in the air or the gas is available for expansion through the turbine. It's a function of fluid temperature and pressure ratio. Those are fixed. The power varies only by mass flow. Purpose of gas turbine inlet cooling. These are the big ones. You want to increase the turbine power output. All right, so think about that for a minute. Typically, now I'm Baker Hughes, and I love Baker Hughes. I work with them quite a bit. If I'm Baker Hughes, I want to sell a whole bunch of gas turbines. They don't want me cooling that air coming down into their turbine. Because if they can sell 12 turbines, that's what they're going to do. Well, if we can cool that air down, maybe instead of 12 turbines, you only need 8, maybe you only need 9. Okay. That's why when you chill down the air, what happens is your mass flow rate increases, which allows your power output of those turbines to increase, which means you don't need as many. Okay. You got to do a system analysis because they're cost for everything. So you look at cost avoidance or maybe getting rid of 2 or 3 turbines to avoid that cost, but then you got to pay for the refrigeration system and the controls and the pumps and the air houses to do all that. So you got to do that evaluation. There is a balance point where it makes sense to do it. Sometimes it doesn't. Okay. So what we're talking about here is combustion turbine power varies directly with the mass flow, same volume of air. Cooled air is denser. The denser the air, colder the air, the denser it is, the higher your mass flow. Greater mass flow increases turbine power. Okay, so basic physics. There are some other factors that come into play, but the big one's temperature. All right, so here's a little chart. And I'll just read here at the bottom here. This is a quote from Mackey, who's very well known in the ASHRAE circles. Increase turbine capacity by reducing inlet air temperature. This results in the air becoming more dense, which leads to higher mass flow rate and pressure ratio. This increased combustion turbine output and efficiency. This increases it. Also, there is a decrease in the heat rate. Remember the heat rate, net heat rate, and reduction in the outlet temperature. The quest for higher efficiency will offset the energy used for cooling the inlet air. Now, when you look at this chart here, what we're seeing is the inlet air, as it reduces, look what's going on to your turbine output. It's increasing. See what's going on here? Now, ISO, remember it's 59 degrees is the normal rating point. So if you can cool that air down here, 2 things are going on. Your turbine output increases. This is your net heating rate. It's decreasing, less fuel. So you can't have your cake and eat it too. You're increasing capacity, reducing fuel consumption. So see what's going on here? Now, for my friends at Baker Hughes, here's another way to look at it. Temperature. Now, this is in Celsius, okay, in kilograms per second flow. As the inlet air temperature is reducing, look what's going on with the flow. It's increasing. Remember, if you increase the flow, you get more capacity out of the turbine. So advantages versus disadvantages. Of course, the advantages I've talked about, but here's a good summary page. You increase the turbine power, get more capacity with cooler air. You decrease the heat rate, less fuel. You extend the turbine life. Well, what do you think happens? You got colder air in, right? I mean, all motors, any kind of motor or rotating equipment, as you gas turbine guys know, and even you ASME guys know, if you can cool that air in or in a motor or a turbine, it lengthens the service life. So you got a side benefit to that. The lower gas exhaust temperatures. Now, there's some heat recovery processes out there where you take that 1,000 degrees exhaust air and you can recover it. Okay, use it in like absorption chillers and do and other processes. So there is an advantage to this. We are lowering the gas temperature, but there is less heat recovery, which is kind of a disadvantage. I've got it under advantages because there is a benefit to lower gas temperatures. So we have less heat recovery, but we've increased the exhaust mass, which can effectively affect the gas temperature decrease. So they kind of all set each other. Possible elimination of water injections, which is used to reduce nitrogen oxide, which is emissions measures that the EPA has been hitting everybody on here lately. You can delay or avoid the need to add additional turbines. Okay, again, I love my friends at Baker Hughes, but they'll get mad at me if they're listening to this. Because this may say instead of 12, you maybe get away with 8. Okay. You can actually, the condensed water from air cooling coils, because you put these big air cooling coils, we bring chill water to them, and then you got like an air house on the inlet side of the turbine. There's a lot of condensate that comes off of those. You can capture that condensate and put it to use. Makeup water, if you have a cooling tower, use it for makeup water. Most of these systems use Ventane coolers, so there is no makeup water. But if you do have a cooling tower, you can use that for makeup water, or if you have evaporative condensers, which is kind of an old school way of turbine inlet air, you can recover it to use it for evaporative condensers. Okay, disadvantages. Usually requires more space. Now, maybe not. I went on and just out of benefit of doubt, I put it on there as a disadvantage. But the reality is you get to factor in the elimination of the space you need for the extra turbines. And in place of those is where you can put your turbine inlet air system, your air house, which is basically cool. It's going to have a little plant for your chillers, some pumping controls. So you may need a stronger building structure to support that. Maybe. It requires additional equipment. Well, again, I'm listing this as a disadvantage, but remember, you just eliminated some turbines. So in replace of the turbines, you're adding some chillers, coils, filters, pumps, piping, wiring, electrical panels, controls. Okay. To purchase, install, and maintain. Well, hell, you got to purchase, install, and maintain the 3 or 4 extra gas turbines too. Okay. So is it really a disadvantage? It depends. All right. Higher air pressure drops due to evaporative media or cooling pools and inlet airstream. That is true. Okay. We have to design the system so that the pressure drops through those coils is pretty low, which means we make sure the face velocity through the coils, the lower the face velocity, the lower the pressure drop. Just like if you're sizing a regular air handling unit, same thing. Instead of 500 feet per minute through the coil or 600 feet per minute through the coil, you get moisture carryover and high pressure drop. You make the coil a little bigger, more face area, reduce face velocity. Condensed water droplets, if you don't size it right, if somebody's designing this, doesn't know what the hell they're doing, then yeah, if your face velocity is too high, 2 things going to happen. Pressure drop's going to go up, and you have moisture carryover, which means just like an air handling unit coil, moisture carryover is going to get sucked in and could potentially damage the compressor blades. So I hardly ever see this because whoever's doing it in the gas turbine usually knows what the heck they're doing. But if they don't, shame on them. That's just basic design. Okay, so with that, I'm gonna get off the heavy metal and kick it over to Robin to talk about milliamp, and then he'll hand it back to me here in a little bit.
Thanks, Batman. So I'm Mike Kennedy. I'm going to be talking about system integration side of this on the industrial controls, and this should be a brand agnostic, project agnostic is the idea here. We're not selling Johnson Controls or anybody else. So everything we do here should be completely applicable. So any project we're doing, sour gas, refineries, process cooling, anything, we're going to have control systems, right? This is the new thing, process automation controller. I don't know when they changed the name, but that's what they call it now. So what all does that say? Here's the art of possible. This is the new milliamp stuff. I don't know if anybody's noticed, but everything's IP. I bet if we look through this room, everything's either wireless or IP. So I love this slide here. This is an IP network. This is Ethernet in most cases. That could be, the media could be fiber, the media could be Cat5, Cat6 cable. But if you look at it, what we do here is we're both dealing with the information technology side and the operational technology side as well. They're all riding on the same piece of media, if you will, whether that be fiber or that be copper. So this is the art of possible. What are we saying? We're saying, I've got this backbone in there, if you will, this network. Why don't I put everything on? Sounds like a pretty good idea, right? The wire's already running where I need it. Why don't I just add on more stuff to it, right? Seems like a pretty good idea. And look at some of this stuff. We go, hey, this looks good. Wi-Fi in here. Look at all this stuff. Network security. If you look through this building or any other building, you're going to see all this stuff in there or above the ceiling here. Right? This makes perfect sense, right? Everything's IP now. So what does that allow us to do? Now I can integrate things in different systems that can talk to each other. And if you'll notice, again, our friend, I used to work for Honeywell, no problem. Hell, may work for somebody else tomorrow, who knows? So everybody can do this. Everybody's using the same backbone. Everybody's using the same media. What that allows us to do is exchange information seamlessly. And that's what we're looking to do. So give you a couple of examples. Fire alarm system. Probably didn't think of this one. I'll give you a quick story. I actually changed one of these out in the building. Huge building. They had it for 50 years. And now it's sitting on an IP network. And they said that the fire department comes every day, because it's a 2 60-story buildings. Fire alarm goes off every day. The fire chief came in after we put all this stuff in there, and he gave me a big hug because it started lighting up on the screen, and it went, the kitchen on the 32nd floor is an alarm. They didn't have to roll out the drawings and go, where is sensor 4216? Because nobody knows. So it allows us to use the same graphics and the same alarming and the same infrastructure that we paid for anyway. We'd already paid for all that stuff, and that works in the industrial world as well as commercial world. So this is, if we're looking at a view of the industrial networking throughout the world, this is kind of a heat map of all the industrial networks throughout the world. Yeah, our friend here sitting at just another day at the plant, right? But how secure is this stuff? You know, it sounds like a really good idea to put all this stuff on the same network, right? But wow, if I do that, got some benefits, but there's some nefarious people out there. I don't know if anybody's heard that before. You know, the best laid plans seem like really good ideas at the time, right? So I'm sure you guys have seen, this is an industrial network sitting there. It's a great idea to put it all on the same backbone, use the same infrastructure, use the same, you paid for the wire, you might as well use it. You paid for the wireless, you might as well use it. However, it does give me some issues. So there are some standards out there that Randy so generously taught us about. The milliamp standards are handled by these guys. Instrumentation Society of America, ISA and ANSI, American National Standards Institute. They published industrial automation standards for control systems. So Johnson Controls happens to be on that list. If you got the things, the handouts there with you, that is actually telling you all about all the people that are on there. So everybody got together and said, let's share best practices and share, we're going to share our ideas and war stories, if you will. So I'm sure everybody's heard about, well, maybe not everybody. There's been a lot of cyber attacks out there. This is one of the very famous ones. We've had, you know, when I started doing this, we never put the high voltage system on the network. Never. The guys I worked with when Randy and I first came out of school, you never put this stuff on the network. And this was right before Y2K, and he was a genius because he didn't have to worry about it. None of it was sitting on the network. After the Y2K deal, it was a little bit more, you know, we understood it a little bit better. So all these standards are trying to do is to give us some best practices, some design things to think about. Why are industrial networks such a problem? I got a lot of soft targets. How many places do I have that people are accessing the network? Could be hundreds, could be thousands. Everywhere I go into a control room, everywhere I go into a marshalling cabinet, everywhere I change media, those are places that I can get in. Those are all soft targets. Multiple entry points. Poor internal network segmentation, and I'm going to show you what that means. That's kind of sounds like a great college word there, right? So let's talk about what that means. Good news is most people have seen this. We got to continue to do it because, you know, what they say, you can't make something idiot proof, only idiot resistant, because they'll make a better idiot if you make it idiot proof. So here's what we're talking about for segmenting the network. So what this says is, I'm not going to go through this and read this for you, but all this is best case scenario. These are best practices. All we're doing is dividing up the process by what they do. So we're only allowing data to flow in certain areas. And the reason that we do that is so that we have less places to put. So this is just a systematic way of laying out the network. And the good news is we don't have to make this stuff up. We had a bunch of really, really smart people that came up with this. There's the standard right there. Like I say, I'm going to run through this or we're going to run out of time. Here's the important part of it. We talked about the IT and the OT part of the world. Red means it's standalone. So most fire alarm systems are standalone. They work on their own. Power can go down. They're going to continue to work. They're still going to call the fire department no matter what. And there's 10%. So they are a bit more, vulnerable. Intrusion systems, that would be your burglar alarms, things like that, access control. And I would submit that, click the button here. These are probably a little bit more vulnerable than is depicted here, because almost all CCTV and access control today are sitting on the IP network. You know, you can pull, I don't know how many people have like a Nest thermostat, or you got a Ring doorbell or whatever comes up on your phone. Well, that's this. How do you think it gets there? It's coming the same way. So what we're saying here is, what's the most vulnerable thing that we got? Building automation and control systems. So it is incredibly important that we do our homework. This is Johnson Controls has a industrial, this is our solution to it. There's lots of them, and this follows those ISA standards, just like what you got there in front of you. Like I say, this is the sales pitch. There's some external data, tells you exactly how we do it, exactly how it should be done. So this isn't rocket science. We thought this out. So kind of switching gears a little bit, we want to talk about technology contracting, and this is a little bit more, this is newer. So as Randy told you, our group gets involved with things that are at feed or at design time. Historically, the way these things worked is each one of these things was done in a bubble, just like what you had there. And what happens when you get all these things designed up, everybody knows, well, nobody talked to each other. The operator doesn't know what, the operator didn't know what the construction guy wanted. The electrical engineer didn't know what this guy wanted. None of these people coordinated with each other. So obviously we have finger pointing, that kind of thing. So here, well, probably over the last 5 to 10 years, we started employing a technology contracting mindset. And there's lots of them. There's a lot of technology contractors and they get involved. We happen to be one of them. There's lots of them. And we encourage most of these big companies to use a technology contractor to simply bring all this stuff together. Owner sits here in the middle. They tell the EPC what they want. Some of them go out and go, let my IT guy do his thing, let the operations people do their thing, let the construction people do their thing, let the service providers do their thing. And none of it's integrated, none of it's on the same network, none of it's following those standards, none of that. So what we have seen here, like I say, over about the last 5 or 6 years is we encourage most of our large EPCs and owner clients to use this technology contracting methodology.
Yeah, Mike, let me insert here just for a
Sure.
second. On this issue, it's a very near dear to my heart in that in the good old days, you've got the EPC, just call them X company. They're procurement guys. We might work with the engineering side for 2 or 3 years, help the engineers solve the problem, put it all together, and then they hand it over to the procurement guys. And it's funny, we can no longer talk to the engineers. Okay, so here comes the procurement guys.
I'd back it up for you.
And the procurement guys, they want to go get pricing on the chillers, refrigeration system, or the turbines, or whatever. Maybe there's some pumps. Maybe there's fan coolers. Maybe there's air houses. There's controls. There, different contractors, construction managers. So the procurement guy goes and gets the lowest, cheapest bid. And then he puts all those components together. It's kind of like you go to Kroger's to get your milk. You go to the Winn-Dixie and get some on my age, get your meat. You go to Piggly Wiggly, yeah, Piggly Wiggly, HEB to get your bread, you get the story, right? So, I call it, let's go Krogering. Okay. So, or another part of the expression, they prostitute the thing out. Make the lowest bid win on everything. Okay, great. The procurement guy did his job. Rah, rah. Then the job goes. Now we're in the first year of commissioning startup. Now you got to take care of the Venture Globals of the world and the Cheniere Energies of the world, et cetera, right? Now you're having commissioning startup issues. Who gets phone call? EPC does, the engineers, not the procurement guys, the engineers do. And then what happens? So the engineers are starting to have a fight with their own procurement people about, hey, we're talking about, now I'll just give an example, Bechtel, $3 billion contract in Australia. You know how much the inlet turbine system cost for inlet air chilling? 30 million. Is that what? 1%?
The whole thing.
1% of their contract. Do you think Bechtel cares if we're getting it from 8 different people or one? Hell yeah, they do, because of risk. Over 1% of the cost, we're going to nickel and dime and get the cheapest thing so that we can get all this risk? No. The world's changing in the way these LNG jobs are going down. Yeah, cost is an issue, capital expense is an issue, but risk is much bigger. You got to do it right. So this coordination of efforts, I don't want to call it sole source. I mean, you can bid a technology contractor against other technology contractors. But the key is that they own it. All the risk is with those guys. You draw the dot around the system, contractor, you own it. I'm not talking about the mechanical electrical, I'm talking about the technology contractor. They own it. If I'm Bechtel, if I'm Kiewit, I'm Worley, hell yeah, that's what I want. Did it cost me 1.2%? Okay. I still got my $3 billion contract. The risk is worth something. And so we're seeing that more and more every day. So go ahead, Mike.
And let me say from the guy who has 2 kids that are lawyers, the lawyers drive this up. You know, risk is a really, 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 very big deal, especially with the state of contracts these days. We got my soapbox there. Here's all the things that a technology contractor can and should help you with. And we'll give you guys a copy of all this stuff.
The blue is everything that technology contractor handles. The brown typically not. Okay, now we're back to heavy metal.
Back to Batman, sorry.
Batman, I got my coat, cape on. How are we doing on time? I can't. All right, so we're running. I'm gonna start talking fast. I might skip some slides, but I'm gonna talk fast. So what I've got is a couple examples, some turbine inlet air chilling, some different approaches. So I'm gonna go through this machine gun fast. So stop me if I'm going too fast. All right, so what we're looking at, that's an LM6000. Actually, that's an OGE, but now it's Baker Hughes, right? So one project that we worked on was really interesting. And due to non-disclosure agreements, I can't give names of projects and all that, as y'all can appreciate. Some that are listed here over in Iraq, as we did one for sour gas treatment. But this is one that we did for one of the local EPCs. And we were now analyzing what we call a direct and indirect system. Okay, the difference between a direct and an indirect is a direct is an air-cooled system where we have air-cooled heat exchangers for heat rejection, versus an indirect is typically centrifugal chillers with either cooling towers or fin fan coolers. Okay, normally fin fan coolers are used when you don't have water makeup. Usually you're close to the ocean, where a lot of these LNG sites are onshore. And so this analysis was centrifugal chillers with fin fan coolers, which is considered indirect. And the direct is we were using air-cooled screw chillers that did not need cooling towers or fin fan coolers. Okay, and then you had to meet all these different requirements. IEC, this is an international job, so I won't get into those gory details.
You may have He's too heavy.
Okay, so this is indirect. I'm sorry, this is direct. What you're seeing, those kind of fuzzy, but what you're looking at is basically a football field of air-cooled package chillers. Okay, and you would think, holy cow. Okay, so we got all these package chillers, and typically package chillers, air-cooled chillers. The largest package air-cooled chillers you can get is if it's 50 hertz power is around 400 tons. If it's 60 hertz power, we get up to about 500, 550. That's the maximum. The maximum voltage is 400 volts, 50 hertz, or 460 volts, 60 hertz. Okay. So in this case, we had a medium voltage coming to the site. And so the analysis was air-cooled chillers, all 400 volts. And then all these little yellow boxes you see are step-down transformers. We were taking, 3,300 volts down to 400 volts. So we got the step-down transformers, strategically located. And then what you see here in the pink are pumping skids, where we had pumps that was pumping the chilled water through the system. I'm not showing the piping interconnections. That's another drawing. But so essentially, we have to space these so that the the two heat exchangers aren't fighting for the same heat rejection area. So you got to space this thing out, both on the side of the units and on the end for electrical clearances, things of that nature. Pumping skids, step-down transformers. This is what it looks like from kind of a pseudo P&ID scheme. In this case, we had 6 turbines. LM6000s, and we'll get into the controls here in a minute. I'm gonna steal some of your thunder. All right, and so with the air-cooled chillers, we had these air-cooled chillers. Remember, air-cooled heat exchanger, which is a fin and tube heat exchanger using air for heat rejection. The evaporator was showing tube heat exchanger, ASME vessel. We had them in series, so we had an upstream and a downstream chiller because we had a pretty wide delta T on the water. The wider the delta T, the smaller your pipe. So we were designing this so we could put it together, but also try to reduce total installed costs. So anytime you can do a wider delta T on water, that's to your advantage. So we had all of the evaporators in series. So that's what you're looking at here. Everything's in series. And then on the pumping, we had N+1, really we had 3 pumps doing the duty with 1 standby, okay, for each bank of chillers. And then at the turbines, we had constant pumping. Now, there's some discussions on that, but constant pumping, we're doing constant flow. And then at the turbines, we'd have bypass. Okay, so it always deliver constant flow. And if we didn't need the water to maintain a certain temperature entering the turbine, we just bypassed it and we brought it back. So basic piping. Controls, with the pump skids, we include all the pumps, the hydronic specialties like buffer tanks, expansion tanks, air separators, etc. But also on the skids that are pre-piped, insulated, jacketed, they're also pre-wired. They have variable speed drives, which even if we're constant flow, we recommend variable speed drives for soft start and for commissioning and start up the system for balancing purposes. Okay, cost of VFDs and motor starters are about the same these days. I see a bunch of guys here with gray hair like me or losing hair like me, both. Remember back in the day, variable speed drives were a hell of a lot more expensive than regular motor starters. Well, with the advancements in technology, the cost for each of those are close to about the same. So from our experience, you put a VFD on there, it's a much better product, soft start, it's pre-wired. We on the skid, we also include the controls. So you would think we're Johnson Controls. Well, when we do these projects, we actually use industrial PLC. So we're partnered with Rockwell Automation. And so we use Allen Bradley systems.
Or Siemens, if you guys like that.
Yeah, or Siemens. Yeah, we can work with Siemens as well. Or even Honeywell Process Solutions. We partner with all of them. But remember, we're system integrators. We do the whole thing. Sometimes it's not always our products, by the way. In this case, we had redundant processors. And this was kind of the design that Milliamp put together. I won't get into the details because we're out of time. But this was kind of on the skid, we had redundant processors. We had some NEMA enclosures with HMI, human interfaces. So that's kind of what the direct approach looked like. The indirect approach. In this case, we had 8 centrifugal water chillers. The evaporators were selling 2. The condensers were selling 2. Now we're using water for the heat transfer mechanism instead of air. Okay, so now we've got selling 2 condenser, all right? So with the evaporators, we still had the evaporators in series. So we had a downstream and an upstream evaporator. So the upstream evaporator took the flow at X temperature, dropped it down part of the way, and then that temperature entered the second chiller, the downstream chiller, and cooled it the rest of the way. That's what went to the process, or the inlet air coils, okay? On the condenser side, we had those in parallel. So what you're seeing here is the blue is chill water, cold, all right? These are your pumping skids for the evaporator side. And then these are your pump skids for the condenser side. Okay, so notice we have 8 chillers, 4 skids for the pumps for the condensers, 2 skids for pumps for the evaporator side. These are the fan coolers down here at the bottom. All right, so again, looks like football field.
What application, what size application is it for?
This was about 12,000 tons of refrigeration.
What size gas turbine?
6 turbines.
6 turbines.
6 LM6000. All right, so that's what that design concept looked like. And then again, the flow concept, again, remember the evaporators are in series. The condensers, which is in red, are in parallel. So you see the fan coolers. And again, we had 2 pumps doing the load, 1 standby. So 2 + 1 concept for each set of chillers.
And the beauty of that is, if we wanted to have the structural steel, we could have stacked them. We could have set them on top of each other, but that's gonna take a hell of a lot of structural steel and cranes and things like that. So we could have reduced the footprint.
Yes,
What kind of differential are you
we'll get in there. All right, again, same approach on the controls. Same identical approach. The only difference is instead of just the pumps and air-cooled chillers, we're doing both chill water and condenser side pumps and the fans on the fan coolers. That's all we're doing, extra points. All right, so here's a comparison. All right, so the indirect approach, 24 chillers. Remember that, all those chillers? 24 of them versus 8 centrifugals, okay? Remember the different heat exchanger types. Both evaporators are shell and tube, but the difference on the condensers was the direct, they were air-cooled condensers. On the indirect, they were water-cooled shell and tube heat exchangers, okay? So if you start looking at, let's start looking at everything. So now let's look at capacity. Based on the air-cooled machines, we can actually dial in the capacity better. We can actually match the load. The actual load requirement was closer to 35, a little over 34. We were right on it on the air-cooled machines, direct. The indirect, we had to oversize just a little bit, 36. And this is in KW, but if you convert it, you're getting close to 10,000 range. Temperatures, we're in Celsius here. We were leaving the evaporators at 3 degrees Celsius, which is, run that number, what is that in Fahrenheit?
36.
Yeah, okay, 36 degrees. Remember, this is water temperature. On this project, all we were doing was the chillers and the fan tank coolers and the pumping skids. We weren't providing the air houses. The air houses is where you bring the cold water to it, and then you got the air going through it, and then it leaves the coils at 40 degrees plus or minus, get it cold. We weren't doing the air houses on this job. Okay, we were just doing the chillers. But anyway, what this analysis is showing, when you look at the different operating conditions and you factor in all the power, okay, the power, the centrifugals, if you look at it in kW per ton for the plant, okay, kW per ton for the plant was 2821 versus 3422. Advantage centrifugals, that makes sense, right? If you look at it from a footprint standpoint, the centrifugals had a smaller footprint than what was required for all the air-cooled chillers. Okay. However, well, let me stop. Which one do you think won this value analysis? Always about the damn money, right? So considerations. Okay. Considerations. Oh, this thing will come on. Yes, you can get that going. So considerations, climate. Okay. Depending on the climate, where you're located, your air-cooled chillers. Thank you. You touch it a certain way. All right, so the climate, an air-cooled chiller, if you have cooler ambient temperatures, your air-cooled chiller would actually give you better energy performance than what's shown here, okay? Fuel cost and availability. Okay, what do I mean by that? Fuel cost is cost of electricity. You would think if we were dealing with a hospital or a school, this difference in kW per ton performance, that's a pretty good number. That's about 50%? No, 25%. 30% difference. That would mean something if you were paying a lot for your energy cost. A lot of these industrial plants, sometimes the energy companies just give them the damn energy just to build their plant there. So a lot of times, believe it or not, that doesn't mean a damn thing. They don't have to worry about their energy costs. Right? So it depends on fuel cost availability, footprint requirements. If you got a tight footprint, yeah, you got to go with the indirect. It's smaller. But what if they got 2 football fields and they have plenty of land? It's not an issue. So it depends. The direct. The disadvantage with the direct, remember, we need a switch gear. We had to go actually 6,600 down to 400. So remember those step-down transformers. You got to have those. Indirect, however, you got the additional piping for the condenser water side. Fan coolers and all those condenser pumps and the electrical associated with it. All that stuff costs money. Indirect need for additional maintenance and parts in the future. All the cooling tower, the condenser fan cooler fans, the condenser pumps and the motors. All the hydronic specialties, more maintenance. Energy costs based on actual runtime hours. All this is at full load. When you got 24 chillers, if you only need 3 operating, last I saw, there's an on-off button. You just turn the other ones off. There is no energy. So really what you got to do is do a full system analysis to see, what's your actual operating profile? How often are you at full load, part load conditions, how many hours, et cetera, and see what your energy consumption is at those points. Then you do your analysis. Okay. Turn down redundancy plays into that. Servicing during plant shutdowns, installed cost. Okay. When you start doing all that stuff, these guys won that particular analysis in this case, believe it or not.
It's also in a part of the world that's a real cool.
Okay, so I'm
Without
gonna-
saying anything else.
how much time we got left on?
-6 minutes.
Moving towards questions.
Okay, so I'm gonna skip this slide. I'm gonna show you a couple of photos. All right, this is again, we're not here to sell York or JCI. Of course, we want you to buy our stuff, but this is an industry independent thing. This is just an example of what a centrifugal chiller looks like. You take the word York off of it. It could be Trane, it could be Carrier, it could be Daikin, it could be, you name it, whoever, okay? In this case, these are some big 3,000 ton centrifugal chillers. This is in Africa. These chillers were designed to be put outdoors, okay? That's why they're all stainless steel, okay? After we already built them and shipped them, the customer decided he was gonna put them indoors. So we built a plant over it, which made no sense to us. Like, shit, you just paid all that money to do all this stuff, then you're putting them indoors. So anyway, these are some pretty big chillers right here. And they're dual compressors and ABB motors. Initially, these ABB motors were also stainless steel housed, but since we went inside, they took the housing off of it. So that's why you can see the motors, big ABB special motors. Okay, so that's that one. And then I'll show you a picture of what
What was the motor horsepower there? 1,700 each.
well, those, no, that was a different project in Africa. I think those were about 2,500 horse each. Those are some pretty big machines.
You don't want to run on 480.
And then this is an air-cooled chiller. Now, notice this is by a support building at the plant, but because sound, air-cooled machines, they use screw compressors. So screws, unlike the old recips will rumble, right? Screws are high frequency. They're directional in sound. So they're screamers. That's what they sound like. Now, that sounds pretty good. Didn't it?
When you unload them there.
Okay. So sound's an issue with screw air-cooled machines. So the way we address that, we put these big, it looks like a German tank. We put sound attenuators. So behind all this, inside that is a chiller. So you got the air coming inside, and then you don't see it, but the fans just charge up. Now, this is an example of one that was put by a support building, but visualize that times 24, and that's what they ended up doing on that other job. Okay, so with that, I think I'm going to, oh, you know what we didn't do? A couple of quick slides and I'm done, Ellen. All right, this, we talked about fin fan coolers when you don't have makeup water available. When you do have makeup water available, and you can go with a traditional cooling tower, then we can put packages together. You've heard of modules. Okay, so we do modular construction where we build a chiller, we put it in a box. Everything's chiller's there, it's pre-piped, it's put in a module, it's put in a house. Above this house, we got 3 cooling towers up above. So this is one, and then the turbine and air house is right here in the back. So this is where you got a completely modular system, put it in a building above its cooling towers. So that's another different approach we use. And then the last one, because we talked about sour gas treatment, this is one in Iraq we did. In this case, we got five, I think these were 500 ton. No, I'm sorry. These were 400 ton chillers. And in this case, we had a custom skid we put together. On this skid, we had 2 evaporator pumps. We had all the hydronic specialties, and then we had a gas to water heat exchanger. And in this case, we were basically taking sour gas. Sour gas was coming into it right here. Chill water was coming in right here. The chill water was leaving right here. And the gas, sour gas, was leaving here. And we were cooling that down with a feed gas. So I want to say we got it down to 65 degrees or something like that. It came in at 100 and something, and we got it down to 65. And so we do a lot of sour gas treatment. A lot of times it's air cooled chillers. There are some that do water cool as well. This is pentane gas, 2 air cooled chillers with pentane gas heat exchanger. Skid here, and then here was a pumping skid with buffer tanks and expansion modules. And again, I can show you a bunch of other examples, but this is one with cooling towers. The two cell cooling tower, big double compressor chiller. And then in this case, they had no redundancy, which was crazy. So they only wanted 1 condenser pump, 1 evaporator pump, yet they wanted 2 cells and 2 circuits on the chiller, but no redundancy on the pumps. And then there was your feed gas heat exchanger. So that one was with a cooling tower. So with that, I'm going to stop because we probably went a few minutes over. So questions, comments? Yeah, we're 9 minutes over, so I apologize for that.
The water used in these systems is all specially treated, right?
On the cooling, if you're using cooling towers, yeah, you definitely want water treatment services. Normally there's chemical treatment
Well,
companies.
even for the water used.
On the evaporator side, yeah, they normally, they'll treat that water, but it's a
The
closed loop system.
right.
Yeah, they'll initially treat it and then they close it up.
Yeah.
And depending on the plant maintenance and if they ever have to access it or whatever, when they go to access it, then they might go to clean it. Normally, when we put the little the skids together, we'll have a pot feeder in there to add some chemicals and treatment on the evaporator side. It's not used often. Now on the condenser side, absolutely, you got to have water treatment. Yeah, Lauren.
Do you have any gas turbine inlet chiller systems here in the Houston region, for examples?
Most of the stuff that my team does is all over the world. Now here locally, there are some plants that have some gas turbines. And probably before my time, we've sold some stuff there that are still running today. I mean, these centrifugals, normally most of them use centrifugals. They use centrifugals, this system lasts 30 years. But they're long lead time. I mean, a long life system.
There are some.
But there are some in the Houston area. I had to get with my industrial team. We have a whole different office up before. That is where all our industrial service technicians and industrial salespeople are. I can call them and I can find out, hey, where are all the plants? We got all this stuff. But most of the stuff Mike and I work on in our team here, man, we're working with Bechtel or Kiewit or Worley on jobs in freaking Norway and Afghanistan, and Iraq and
They're never in
Australia,
the tropical islands or anything like that.
Trinidad.
Because they're putting in
India.
8 LM6000 right down on 288 in Rochelle.
Yeah. You know, the real people you ought to ask that question to is Clayton Finley over at Baker Hughes,
I don't know.
Bob Simon.
Yeah.
Those guys, they'll tell you. We work with them quite a bit. But they would probably know before we do. And of course, we don't do all the projects. I mean, Train gets some, Carrier gets some, you know, they could, but Baker Hughes, hell, they're the leader in the gas turbines. So they have probably 80% market share. And so they could tell you, some of them have inlet turbine chilling, some of them don't.
Depends on whether they're peaking plants.
Yeah.
Okay, thank you.
Okay.
Very good presentation.
Any other questions?
If you need a PDH, you're on the table.
Yes. Yeah.
Technical question, but go back if I look at the slide
Which line?
You referenced the rock, it was the.
Basra. It's the largest gas field in the world. Somebody said had a chat here.
Oh, I asked if anybody had.
Oh, any questions? Oh, okay. All right, let me minimize that and then see if I can do this. Mike.
Man, this is, you don't have electronics on you. Yeah, I was gonna say, it's just not holding his mouth, right?
All right, I'm gonna go old school here.
Try to page up. button, yeah.
Previous, 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 previous. There, that one. Now that was Monsoon Sour Gas Treatment Facility. That's the Basra Oil Company, Republic of Iraq. That's the largest oil field in the world. We did that one, and then there's another one called the AMET Sour Gas Treatment Plant as well. We did it as well. It had 3 chillers. This one had 5, so I showed this because it was more impressive.
Must have been a challenge to deal with all that sand in the environment.
You'd be surprised. You'd be surprised. But yeah, that is an issue. We do have to factor that in. There's a D-rate factor for it. So not only do we have to maintain, in this case, we need to maintain a little over 3 meters, which is what, about 10 feet roughly. Okay, so we need to maintain about 10 feet between it so that these condenser fans aren't fighting for the same heat rejection. You got head pressure problems. Okay, but the actual distance in a normal application is only 8 feet. But because of the sand potential, we add another 2 feet to it. And then the maintenance, so a maintenance contract with it, which are, normal maintenance, you clean air cooled chillers, you clean up over there, you got to do it like, instead of monthly, you got to do it almost weekly. Especially if they have sandstorms, which we never see here, but over there. That answer your question? Anything else? All good?
All good.
Okay, beautiful. Now, Mike and I were told, we were never here. All right. So we were told that our alarm system kicks on at 9 o'clock. And if we're not out of the building, all hell breaks loose. The police, the fire alarm, everybody comes here.
However, I see a lady cleaning.